The other day I was browsing the internet and came across a professional SolidWorks certification exam. These exams are usually meant to prove your skills and boost your resume. And I thought, what if I tried to take it but using FreeCAD instead of SolidWorks? So in this video, I'll show you step by step how I managed to complete the test entirely in FreeCAD, and maybe I'll convince you that FreeCAD has become powerful and mature enough to take on this kind of challenge. So let's get started and jump right into it. To follow along, you can download the exam PDF from the link in the description. The first few pages explain how to use the software for the test, but what we're really interested in is the actual exam, which starts on page 18. The first thing to do is take a good look at the part, because the first question will be to recreate it. Since this is a time test, and given the shape of the part, you need to quickly identify the key features of the model. Looking at the dimensions, you'll see that some are numbers and others are letters. The ones labeled with letters represent variables. We'll be asked to modify them later so our model updates dynamically. We can see the letters A, B, C, D, E, F, X, and Y, so we'll need to create 8 variables to control our file. Scrolling down a bit to see the questions, we can see the values of the variables we need to use to answer the first one, which is to determine the weight of the part based on those values. We can also see that variables from A to F are values we need to enter, while X and Y are calculated ones. So let's start by creating these variables in FreeCAD. Before that, we need to create a new body. Click the new body icon in the top menu, then click the varset icon to create our variables. Let's start with variable A. In the name field, type A, then in the value field, enter 213 mm. You can then press enter to create a new variable. Next, create variable B and set its value to 200, then keep going the same way until you reach variable E. For this one, we can't name it E because that's reserved as a constant, so instead name it E1 and set the value to 41. As for constant F, it's a variable that represents a standard hole size. Since this value is only needed for the first exercise and won't change, we don't actually need to create it. So we can move straight on to variable X. Unlike the other variables, this one is defined by a calculation. To set it up, click the FX icon at the end of the field. In the expression editor, we need to specify that we want variable A divided by 3. To do this, either select the variable by typing varset and picking A from the drop-down menu, or simply type A in the field. It should find the variable automatically. Then type /3 and click OK to confirm. In the value field, you should see 71, which is 213 divided by 3. For variable Y, we'll follow the same process. Click the FX icon in the value field again. In the expression editor, type B/3 plus 10 mm. Make sure to include at the end, otherwise it won't work. Click Add or press Enter to continue, then click Cancel to stop creating variables. In the data properties of the varset on the left, you should now see all your variables listed, giving you quick access to each of them. We can now start modeling the part. It's a pretty typical shape for a modeling exercise. If anyone knows what it's actually called or what it's used for, feel free to drop it in the comments. Because right now, I'm kinda like Ray Charles. I have no idea what I'm looking at. Usually, when you have a part to model, the first step is to identify its base shape, the primitive form you'll build everything else from. Here, the base shape is the plate with dimensions A and B. So we will start by creating this part. We could make this plate using the cube tool, but I prefer the workflow of starting with a sketch and then extruding it. So click on the sketch tool in the toolbar. In the viewport, you'll see the 3 origin planes of the part. Since we'll be extruding along the Z direction, the height, we're going to click on the blue XY plane. The view will automatically rotate, so you're facing the plane straight on, just like drawing on a sheet of paper. Since the shape we need to draw is a rectangle that we'll later extrude, we'll use the rectangle tool from the menu. Here, it's really important to start your sketch right at the origin. You should see a red cross indicating the exact center. Click once to place the first point there. Then move to the right and click again to place the second point in the top right corner. Now we're going to set the rectangle's dimensions and assign them to our variables A and B. Following our plan, the vertical dimension corresponds to variable A and the horizontal one to variable B. To do that, we'll use the dimension tool located in the constraints toolbar. Click on the vertical line, then click to the left of it to place the dimension. To assign a variable, click the FX icon to open the expression editor. To call the variable, start by typing varset then A. It should appear on the screen. Press Enter to accept, then press Enter again to close the expression editor. We need to repeat the same process for the horizontal dimension, but this time assign it to variable B. You should see the sketch turn green, which means it's fully constrained. The dimensions should be orange, indicating they are driven by variables. Once that's done, click close to exit the sketch. Now we're going to extrude the sketch. If we check the drawing, we can see that the extrusion depth should be 25 mm. So, with the sketch selected, click on the pad tool on the right. In the panel that opens, type 25 in the length field, then click OK or press Enter to confirm the creation. Alright, nice job. Now we're going to model the central part of the piece, the section that cuts through the middle. On the drawing, we've got both its dimensions and its extrusion height. To draw the sketch, we can either use the top face of our part. In that case, we'd need to subtract 25 from the extrusion height, or like before, sketch on the XY plane and simply extrude by 95 mm, as shown in the plan. I'll go with the second method because I still remember what my teacher used to say. Always use the values from the drawing, never make up your own, even if sometimes it makes things a lot harder. Following that wise old advice and out of respect for our elders, let's start by hiding the pad operation in the tree view by clicking the little eye icon next to it. Then we'll use the Create Sketch tool. Next, select the XY plane as the sketch plane. For our sketch, we'll use the part we already created as a reference. So go back to the tree view and make the pad visible again. From the drawing or 3D view, we can see that this middle section aligns with the edges of the base plate. In FreeCAD, we need to project those edges into the sketch to use them as references. To do that, use the External Geometry tool, then click on the right edge. That creates a magenta line, which means it's a projected edge. Since we're only using it for reference, select the line and click the Construction tool to turn it into a construction line. We can now start our outline following the drawing. To do that, we'll use the Polyline tool, which lets us draw it all in one go. Start your sketch by snapping to the projected line on the right, then draw a horizontal line. You should see a small red symbol next to it. That's the horizontal constraint indicator. Next, according to the drawing, we need to create an arc. We can do that directly with the Polyline tool. Just press the M key 4 times and it'll switch to arc mode so you can draw it right away. Click once to place the point, then press M again to switch back to a straight line. Draw a vertical line going down until you reach the red axis. Right-click or press Escape to stop using the tool. Now we're going to apply some constraints to our sketch. First, we can see that the bottom point isn't constrained to the red axis. To fix that, select the point, then the red axis, and click the Coincidence Constraint tool in the toolbar. Next, we need to make that line vertical. Select it, then apply a vertical constraint using the Constraint tool. In the drawing, we can see that the horizontal and vertical lines are equal, both measuring 80. So select the two lines and apply an equality constraint to them. Next, select the horizontal line and, using the Dimension tool, set its value to 80 mm. Now we can set the height of the horizontal line. It corresponds to variable c, as shown in the drawing. To do that, use the Dimension tool to create a height constraint. Then click the FX icon and in the expression editor type varset c. Then press Enter to confirm. Now we'll create a 15 mm offset of this sketch, as shown in the drawing. To do that, select the 3 lines and use the Offset tool. In the panel on the right, change the mode to intersection and check the Add Offset constraint box. Then type 15 to create the offset. This creates an offset on both sides, but we only want it on the right. To fix this, select all the left side offset lines and use the Construction tool to turn them into construction lines. Now all that's left is to close the contour. Use the Line tool to draw a line at the top to close the shape and another line at the bottom to fully complete it. You might get an error message saying there are redundant constraints. No worries. Go to the constraint settings and make sure the Auto Remove Redundant Constraints box is checked and everything will be fine. You can now exit the sketch by clicking Close. In the panel on the right, select Pad to create an extrusion and enter 95 as the value, just like in the drawing. Before we go any further, let me introduce the sponsor of this video, PCBWay. They're a trusted name for both DIY and industrial projects. I had the chance to test their 3D printing and CNC services to create a bike chainring, and the quality was truly professional. You simply upload your 3D file, select your options, and you're set. Their standard 3D printing options are excellent. Plus, every new customer receives a $5 coupon for their first order. A big thank you to PCBWay for supporting this video. At this point, we could go in a few different directions. Either model the 2 cylinders or the whole placement. Here we're going to start with the 2 cylinders. On the drawing we can see that the 2 cylinders are offset by 10 mm from the edge of the part and their length corresponds to variable d. So to create this, we'll first make a plane parallel to the face of our part with an offset of 10 mm. To do this, select the face of your part, then use the Datum Plane tool in the task panel on the right. Still in the same panel, scroll down to Offset in Z direction and enter 10 mm. You can then rotate your 3D view to make sure the plane has shifted in the right direction. If it hasn't, you can use the Flip Side option to correct it. Next, select this new plane, then click on the Create Sketch tool. Looking at the drawing, we can see that the cylinder is positioned 7.5 mm from the edge, which is actually halfway. We also see that the cylinder's outer diameter corresponds to variable x. So we'll use the top edge of the wall as a reference. To do that, use the External Geometry tool to project the top edge into our sketch. Then select that line and turn it into a construction line using the Construction Mode tool. Now select the Circle tool and draw a circle centered in the middle of the line. You should see the constraint icon appear near your cursor when it snaps correctly. Grab the Dimension tool to set a diameter for this circle. Click the FX icon and in the expression editor type varsetx, then click OK to confirm. We can now exit the sketch. Next, use the Pad tool to create an extrusion. Click Pad in the task panel. If the extrusion goes in the wrong direction, check the reversed box in the pad parameters. Then in the length field, click the FX icon, type varset_d in the expression editor, and click OK to confirm the operation. Now we'll create the central hole in the cylinder. On the drawing we can see that the hole's diameter corresponds to variable e. To do this, select the Datum Plane and create a sketch on it. Using the External Geometry tool, select the edge of the cylinder to project it into the sketch. Then select this circle and turn it into a construction line. Next, use the Circle tool to draw a circle concentric with the dashed construction circle. Then use the Dimension tool to assign it the value of varset E1 and click OK to confirm. We can now exit the sketch. In the task panel, select the pocket operation. Still on the right, change the type to Through All, then click OK to confirm the operation. Great, now we're going to do exactly the same thing for the other cylinder. As we can see on the drawing, it's positioned the same way, but its diameter corresponds to variable y. Since it's exactly the same process, I suggest you pause the video and try it yourself as a little exercise. I'll speed things up on my side, but if you get lost, you can always slow down the playback in your player. While we take this little break, I'd like to hear a bit more about you. Is FreeCAD your first modeling software, or have you used others like Blender? Or are you a CAD veteran coming from SolidWorks or Fusion 360? And most importantly, what do you think of FreeCAD so far? For me, I learned CAD on Creo, and I find that nowadays FreeCAD works quite similarly to Fusion, SolidWorks or Onshape. There are still a few precautions to take when modeling with FreeCAD, but it's becoming an increasingly credible option. I'd love to hear what you think about it. Now we're going to add the small chamfers on the inner diameters of the cylinders. On the drawing we can see they're 2 mm chamfers at a 45-degree angle. To do this, select the 4 inner edges of each cylinder while holding Ctrl. Once they're all selected, click the chamfer tool in the task panel. In the Size tab, enter 2 mm, then click OK or press Enter to confirm. Now we'll add the small fillets on the base plate. As shown in the drawing, these are 10 mm fillets. Just like with the chamfers, select the 4 edges of the plate while holding Ctrl, then click the Fillet tool in the task panel. Then enter a radius of 10 mm and press Enter or click OK to confirm. Now we'll model the small extrusion on the corner of the part, along with the hole that goes with it. As shown in the drawing, the total extrusion height is 35 mm from the bottom of the part. To start, hide the fillet operation, then create a sketch on the XY plane. We'll use the edge of our part as a reference. To do this, project the right edge of the part as well as the fillet edge. Then select the vertical edge and convert it into a construction line using the Construction tool. Next, using the Polyline tool, we're going to draw the outline of the extrusion. Start from the highest point of the fillet, then draw a vertical line, a horizontal one, another vertical line down to the red axis, and finally a horizontal line back to the fillet. Then with the Dimension tool, we're going to set a horizontal dimension of 60, as shown in the drawing, and a vertical dimension of 60 as well. The sketch is now fully constrained, so we can go ahead and close it. We're now going to extrude it by 35 mm, just like in the drawing. Click on the Pad tool in the task menu, then on the left side under the length field enter 35 mm and click OK or press Enter to confirm. Now let's take care of the hole. To do that, select the top face of the extrusion, then create a new sketch on it. We'll place a point in the middle of the face. That'll be the center for our whole operation. To find the center, use the External Geometry tool and project the 2 diagonal points of the square by clicking on them. Right-click to stop using the tool, then select both points and turn them into construction points so they won't interfere with the operation later. Using the line tool, create a line between these 2 points. This will help us find the midpoint. Finally, convert it to construction geometry. Next, grab the point tool and place a point on the line's center. A red constraint symbol will appear. Click to confirm and your point is now perfectly centered. You can now close the sketch. In the right task menu, click the hole operation. In the exam PDF, we can see that the hole dimensions refer to a variable called f, but that variable doesn't actually exist in the test, so we can just enter the values directly in the operation. It's a counterbore hole, which means it's made to hide the screw head. The head diameter is 30 mm, the depth is 10, and the hole goes all the way through with a diameter of 15 mm. So in the right panel, set the head type to counterbore and the depth type to through all. For the head diameter, enter 30 mm, head depth 10 mm, and diameter 15 mm. In the viewport, you'll see a red preview. Once you're sure the values are correct, click OK to confirm the operation. On the drawing, we can see there's a 15 mm fillet on the inner edge of the extrusion. To do that, select the edge, then click the fillet tool in the right panel. In the radius field, enter 15 mm, then press enter to confirm. Now we just need to make the inner cutout. On the drawing, we can see there's a 9 mm offset from the outer edge and a 5 mm thickness from the bottom face. To keep things simple, and since it won't affect the final result, we'll make the pocket from the top face and remove 20 mm. I know my old teacher would probably freak out if he saw that, but luckily I don't think he's watching this video. So select the top face, then click the Create Sketch tool. We're going to project the inner face to get its edges, so we can create an offset. To do that, use the External Geometry tool, then select the face. You should see the outlines appear in purple. Select all of them, then convert them into construction lines. Select them all again, then click the Offset tool. In the right panel, set the mode to intersection, check the box Add Offset Constraint, then enter an offset of -9 mm. After that, click Close to exit the sketch. In the right panel, click the pocket operation, enter a length of 20 mm, then click OK to confirm. All that's left is to add fillets on the inner vertical edges of the opening. On the drawing, we can see they're 10 mm fillets, and there are 6 of them. In the viewport, hold Ctrl and select all 6 edges, making sure not to miss any. Then, in the right panel, click the fillet operation. In the radius field, enter 10 mm, then click OK to confirm the operation. Great, we finished modeling the first exercise. As you can see, nothing too complicated. Everything went smoothly using FreeCAD. If we go through the exam questions one by one, first create the part in SolidWorks, that's done. Next, we have the material properties, which we'll enter later. All the variables are created, except for f, which isn't really a variable. The question is, what's the mass of this object based on its material? To find that, we'll use a macro in FreeCAD called fcinfo. If you don't have it, you can download it in the add-on manager. To do that, click on Tools, then Add-on Manager. In the search field, type fcinfo, then click Install. You should see a new icon appear in the toolbar. To use this macro, first select your body, then click the icon. A new panel should open on the right. In the Density tab, set it to 7.7 as stated in the exam, and you should see the mass of your object in the box next to it. We get 14,207.34, which matches answer D exactly. At the end of the PDF, we get the answers and can see that D is the correct one. The second question is to change the variable values and see what weight we get. This helps check that the variables are set correctly and that our 3D model regenerates properly without errors. So let's adjust these variables. In the tree view on the left, click on the varset object, and in the properties, you should see all our variables. We'll adjust them according to the PDF values. A to 225, B to 210, C to 176, D to 137, E1 to 39, while F, X, and Y remain unchanged. Next, select the body again, and in the right panel, you'll see a mass of 16,490.46, which is the correct answer. I hope you'll forgive the 0.01 gram difference. The third question works the same way. You need to change the variables and determine the mass. I won't go through it here, you can try it yourself, but I'll just show that I get the correct result of 15,100.46. Again, forgive the 0.01 gram difference. The second part of the test is a bit more interesting. Here we're asked to modify certain features of the part by removing some and adding new ones. If we look closely at the drawing, we can see that we need to remove the inner cutout, remove the small extrusion, create 2 new openings, and make a lightning cut on one of the 2 cylinders. We also need to remove the whole operation. Since we're starting from the same base part, let's first save the file as E1. Once it's saved, we'll do a save as to create a copy and name it E2. With the E2 file open, first close the macro panel on the right. Then, in the tree view, delete all the operations up to the chamfer. Select them one by one, then press delete on your keyboard. Also make sure to delete all the sketches that were linked to these features. After deleting all that, you should be left with this part. We'll start by creating the opening on the right side of the part, as shown in the drawing. It's offset 9 mm from the edges. We'll use the same technique as before. Select the face, then create a sketch on it. Next, use the external geometry tool and select the right face. Once projected, select all the lines and convert them into construction lines. Then select the lines again and click the offset tool. In the right panel, set the mode to intersection, check the add offset constraint box and enter a value of -9 mm. Then close the sketch. In the right panel, click Pocket and in the Length tab, enter a value of 20 mm. On the drawing, we can see the inner edges have 10 mm fillets, just like the previous part. To do this, hold Ctrl and select all the edges, then click the Fillet tool in the right panel, enter a radius of 10 mm and confirm. Now we'll create the opening on the other side of the part, as shown in the drawing. This time it's not a simple offset, we'll have to draw it manually. To do that, select the face, then create a sketch on it. We'll start by projecting the edges that will help us create our offset. To do this, use the external geometry tool and click on the top edge and the arc. Then select both lines and convert them into construction lines. The goal is to redraw the opening. To do this, use the polyline tool and, starting from the bottom, draw a horizontal line, then a vertical line, then another horizontal line, and finally a vertical line. We'll recreate the arc by pressing M several times to get the arc tool, then connect it to the starting point. Next, select the horizontal line and the arc, then apply a tangent constraint to create a smooth transition. Select the two origin points of the arcs, then apply a coincidence constraint. Next, use the dimension tool to create a measurement between the dashed line and the horizontal line and set it to 9 mm. Do the same to set a 9 mm dimension between the vertical axis and the vertical line and also for the offset between the two arcs. Everything is fully constrained, so we can exit the sketch. Then, in the right panel, click the Pocket tool. In the Length tab, enter 20 mm, then confirm. Just like for the previous opening, the inner edges need 10 mm fillets, as shown in the drawing. To do this, hold Ctrl and select the edges, then click the Fillet tool. In the Radius tab, enter 10 mm, then confirm. Now we'll create the opening on the cylinder. On the drawing, we can see the opening should start 30 mm from the edge of the cylinder, and the diameter should be 10 mm smaller than the cylinder's outer diameter. To do this, we'll create a new plane using the datum plane we already made. Make it visible, then select it, and in the right panel, click Datum Plane. In the right panel, scroll down and in Attachment Offset in the Z direction, enter 30 mm. You'll see the plane shifts the wrong way, so check flip side, then confirm. Now select the new plane, then create a sketch on it. To make it easier to see, go to the Tree View and hide Datum Plane 2. Zoom in on the cylinder area, then use the External Geometry tool to project the cylinder's outer edge and the two vertical lines. Next, select these three lines and convert them into construction lines. Using the Circle tool, draw a circle with its center, coincident with the projected circle's center. Then, using the Dimension tool, set a 10 mm distance between the two circles. Using the Line tool, draw two vertical lines starting from the intersections of the circle and the projected lines. The goal is to make them coincident with both the intersection points and the green circle. Using the Arc tool, recreate the outer arc by placing the first point at the center, the second at the left end, and the third at the right, not the end. It could create problems. Then select the arc's endpoint and the vertical line and apply a coincidence constraint. All that's left is to delete the small green segment. To do this, click the Trim tool, then select the segment. It should disappear completely. Then close the sketch. In the right panel, click the Pocket tool. Then, as shown in the drawing, set the length to 30 mm. Don't forget to check the reversed box if the pocket goes in the wrong direction, then confirm the operation. Just like in the previous exercise, we need to add 10 mm fillets on the four vertical edges of the part. To do this, hold Ctrl to select the edges, then click the Fillet tool. In the Radius tab, enter 10 mm, then confirm. Congratulations! You've finished modeling the part for the second exercise. Now we need to check for errors and make sure the model regenerates correctly when we change the variables. In the question 4, we are also asked to change the variable values. To do this, click on Varset in the tree view to access the variables, then adjust them according to the question: A to 221, B to 211, C to 165, D to 121, E 1 to 37. You also need to change the expression for Y. Instead of +10, set it to +15. Click the FX icon, replace +10 with +15, then confirm. Now we can check the mass. To do this, select the body in the tree view, then run the macro. We see a mass of 13,203 grams, which is close to the expected value, but we're missing 3 grams. Where did those 3 grams go? I'll tell you. They come from the chamfer, which wasn't the same as in exercise 1. It's the only thing that changed and wasn't assigned a variable. My theory is that some grumpy old math teacher snuck in here to purposely trick us. We've all had that math teacher. No big deal, let's go ahead and adjust the chamfer value. First, close the macro window, then in the tree view, double-click the chamfer. In the right panel, change the type to distance and angle, set the angle to 30 degrees, then confirm. Then select the body again and rerun the macro. And now we can see that we get the expected value. To answer the last question, just adjust the variables according to the values given in the question, and you should get the correct result. I'll fast forward this part, but it shouldn't cause any trouble. We're reaching the end of the video, and I hope that through this one I've shown you that FreeCAD is a serious and capable piece of software, powerful enough to handle an exercise that's part of a professional SolidWorks certification. We didn't really face any major difficulties getting there. Thanks a lot for watching. Feel free to let me know in the comments what you'd like to see in a future video, and don't forget to subscribe if you enjoyed the content. Thanks again for watching.